let's dive in. At the end of the session, you will understand what is quantum computing. Imagine a world where we solve most complex problems in a second. Problems that would take today's supercomputer millions of years. This is not a science fiction, it's a promise of quantum computing. So, hello everyone, my name is Kiran Patil, and today I will take you into the exciting journey of the quantum computing. This technology leverages us with the principles of the quantum mechanics, which will change the way to compute. By the end of this session, you will understand what is quantum computing, how it compared with the classical computing, what are the concept of qubits, what is the foundation of quantum computers. So let's dive in. So you can see on a screen this is an quantum computer. So what is a quantum computer? It is made of the quantum circuits. Now you might think what are the quantum circuits, right? So firstly, we will understand what is a quantum computing. So, what is a quantum computing? It uses the fundamentals of the quantum mechanics and quantum physics for the computing. As we know that in classical computers, we are using bits, that is zeros and ones for the computing. Here in the quantum computer, we are going to use the qubits. Now, what is this qubit? So, before go to the qubit section, firstly imagine flipping a coin. Now, when you flip a coin, it either head or tails, right? But in the world, the coin is spinning in the air. It's both heads and tails until it lands, right? So this phenomena is known as a superposition. Is this is one of the key principle behind the quantum computing. So when the qubits, when the bits are in the superposition, these are known as the quantum bits, that is a qubit. So how this qubit look like? Now you can see classical bits, that is 0 and 1, and this is an qubit. As you can see, this qubit is representing two states. So as shown in this diagram, you can see these are the classical bits 0 and 1, and these are the qubits gate 0 and gate 1. Now what is this gate? Gate is the Dirac notation. The qubit is represented by this simple gate. This is a gate 0, this is a gate 1. Okay, so qubit is an quantum equivalent of the classical bit. It can be exist in two basic states. One basic state is 0, gate 0, and second basic state is a gate 1. It can also exist the combination of both the states. So combination of this both states is a gate 0 plus gate 1 divided by under root of 2. So this is an qubit. Representation of the qubit. So you can see this visualization of qubit. When it is on a z-axis, it is representing a gate 0. Negative z-axis, it is representing the gate 1. And this is the combination of gate 0 and gate 1. Now we will compare the quantum computing with the classical computing. So to compare quantum computing with the classical computing, firstly the representation of the bits in the classical computing, it's 0 and 1. These are known as the states of the classical computing, state 0 and state 1. In quantum computing, it is represented by the qubits. So these are the qubits, gate 0 and gate 1. These are the states of the qubits, which are nothing but the unit vectors. So the superposition of this unit vector is represented by the alpha gate 0 plus beta gate 0. Now what is this alpha and beta? Alpha and beta are the complex number, and it is showing the linear combination of the Kate 0 and Kate 1. Now, when we are representing the bits in the classical computing, we are representing it in the curly braces 0 and 1. Now, how to represent the quantum bits, that is a qubit, that is a Kate q is equal to alpha Kate 0 plus beta Kate 1. Now, next difference is state of the classical computing is a deterministic, and state of the quantum computing is a probability probabilistic. So what is the probability of getting Kate 0, that is a alpha square, and what is the probability of getting a Kate 1? Now how this probability is calculated? Understand this thing. Suppose I want to calculate the probability. Now I want to calculate the probability of Kate 0. So there is one rule to calculate the probability of Kate 0. Just a second. So to calculate this probability, we are using the bond rule. Now what is this bond rule? So bond rule is one of the postulate of the quantum mechanics, which tells us that probability of any unit vector is calculated by measuring the specific outcome of that quantum state. So here that specific outcome is alpha. So the probability of Kate 0 is alpha square. In next lectures, we are going to see that how this alpha square is calculated using the bond rule. So now next difference is, now we know that in classical computing, the gates are used for the computation. Now you can see over here, this is a NOT gate. Now what this NOT gate does, if we are giving the input as a 0, if we are giving the input as a 0, we are getting the output as a 1, right? So when we are giving the input as a 0, we are getting the output as a 1, right? Similarly, in a quantum computer, there is a poly X gate which works as the classical NOT gate. So if I am giving the input as a Kate 0, I will be getting output as a Kate 1, right? So this is a poly X gate. So the gates in the quantum computer is shown as this square bracket. Then next difference is classical computing uses the Boolean algebra. Now what is this Boolean algebra? Boolean algebra. In this Boolean algebra, for example, we are using a NOT gate on a 0. We are getting 1. It works in a true false or zeros and ones. So as we can see, the output of not 0 is we are getting not 1, not 1 we are getting a 0. Here in a quantum computing, we are going to use the linear algebra. Now how this linear algebra works? Now here you can see the representation of the matrix representation of the quantum gate, that is a poly X gate. So you can see it is represented in a matrix form. So how the linear algebra works? So how the linear algebra works? You can see when I'm going to operate the X gate on the gate 0, when I'm going to operate the X gate on the gate 0. Now what I'm going to do over here, simply I will write the matrix form of the X gate and multiply it with the matrix form of the gate 0. So gate 0 is given in a matrix form like this 1 and 0. So when we will multiply this both matrix, we are getting the output 0 and 1. So this is a matrix representation of the gate 1. So as I told you, when I am going to give an gate 0 as an input to this X gate, I am getting the output as a gate 1. Similarly, if I am going to apply the X gate on the gate 1, then after multiplying this X matrix with the gate 1, I am getting the output as a 1 0, which is a matrix representation of the gate 0. So these are the main differences of the classical computing and the quantum computing. Then next difference is, now we know that in a classical computer the output is irreversible. As shown in this diagram, if you can see, B1 and B2 is the input to the AND gate. So whatever output I am getting over here, it is irreversible. I cannot reverse this output to the input. I cannot convert this output to the input. But in the quantum computer, when you are giving the multiple inputs, we are getting the multiple outputs. So it is easily reversible. So next difference is operation of the classical computing is a reversible that we have seen with the example AND gate, and operations in the quantum computing is a reversible that we have seen uh, with this example. Now, state space required to the n state space size required in the classical computing is a n, which is a linear in size of input, but state space required in a quantum computing is a 2 raised to none. It is the exponential size of input, right? This is why, because the representation of the qubit is in a form of the matrix, as we have seen, Kate 0. Kate 0 is given in a matrix format. Kate 0 is given in the matrix format like this. Kate 0 is equal to 1 0. It is taking a two state space, right? So that means it has a 2 raised to n state space required, right? Because we are representing only one qubit with the two state space. So this is all about the comparison of the quantum computing and the classical computers. So in next session we will see the basics of the quantum computing. In that I will cover the notations which we are going to use in a quantum computing and some of the quantum mechanics concept. Thank you all.